Assalamu alaikum everybody to lecture number 6 about aperture antenna. In this lecture we'll be talking about radiation from aperture. We'll start by talking about some principles used for finding the radiated field from aperture antenna. Then we apply those on our problem to get the radiation equation. Then apply our radiation equation to find out the radiation from rectangular aperture as well as circular aperture. After that, we'll stop here. This is the part that will be covered by our course. The remaining part is for you to read if you are interested in further acquaint information about aperture antenna. So the first part here, just remind you what is aperture antenna. Aperture antenna is most of the time a flared or expanded part of a waveguide, rectangular waveguide or circular waveguide, or even like a waveguide without flaring or without expansion. The main theory that is used to find the radiation from aperture is the field equivalence principle. The field equivalence principle is sort of like an advancement or a modification or like rigorous formulation of Huygens principle, which is, I think many of us had studied this in physics or in optics or like maybe in high school or first year of education. Anyway, Huygens principle is stating that each point on a primary wavefront. So a wavefront is a surface of equal phase for any wave. So each point on this wavefront can be considered as a new source of a secondary spherical wave. So any point on this wavefront can be considered as a point source that is emitting spherical wave. And the secondary wavefront or the progressive wavefront can be constructed as the envelope of those secondary spherical waves. So if at time t we have this wavefront, this surface of equiphase, every point on this surface can be considered as a secondary point source that is emitting a spherical wave. And to find the new wavefront after time delta t, we just go for the envelope of those spherical waves, secondary spherical waves. So you can see things are progressing over time to a bigger and bigger surface, which is expected for a radiated wave. But this principle will be used heavily when we talk about radiation from aperture. The second very important theorem is uniqueness theorem. Based on uniqueness theorem, we can state that a field in a lossy region is uniquely specified by the sources within this region. So if we have a region, which means some volume surrounded by a closed surface, the field in this lossy region is uniquely specified by the sources. We know that the sources in our case is either magnetic current, which is an equivalent source, or electric current, which is a real source. So sources within this region plus the tangential component of the electric field over the boundary, over the surface surrounding this region. Instead of the tangential component of electric field, we can use tangential component of magnetic field over that boundary. Instead of that, we can take the tangential electric field over a part of the boundary and the tangential magnetic field over the rest of the boundary. So this is the words of uniqueness theorem. Of course, we're gonna study it more and give examples and application of it. And here we can notice that we didn't impose any condition on the boundary, any boundary condition on the normal components of the field. Because if the tangential component fulfill the required boundary conditions, Maxwell's equation will guarantee that the normal component also have the proper behavior or proper value over the surface. So, in other words, putting conditions on the tangential component in this case is enough. The equivalence principle, which is based on the previous two principles, Huygens principles and uniqueness theorem, is stating that the field outside an imaginary closed surface, any closed surface is surrounding certain volume, the field outside an imaginary closed surface are obtained by placing over the closed surface, which is the boundary, suitable electric and magnetic current densities which satisfy the boundary conditions. So we know that electric current density, surface electric current density, is related to the tangential magnetic field. In the same way, as we're going to show in details, magnetic current is related to the tangential electric field. So electric and magnetic current densities on the surface are directly related to the tangential components of electric and magnetic fields. So those current densities, electric and magnetic, again, electric current is a real source, magnetic current is an equivalent source. Those current densities are selected so that the fields inside the closed surface are zero. Outside the closed surface, they are equal to the radiation produced by the actual sources. We're going to see the application of that. And this technique can be used to obtain the fields radiated outside closed surface by sources enclosed within it. And so here, the boundary conditions that we are talking about here is N, which is the normal to the surface out of the volume. So this is going out of the volume. E2 is the field at the outer side of the volume. E1 is the field in the inner side of the volume. And this is the first time we see a definition for magnetic source or magnetic current. This is the magnetic surface current is equal to minus N, the normal to the boundary, cross, because it's a cross, we are talking about the tangential component. Normal component will be cancelled out because normal cross normal will equal zero. So even though we are writing down the total field, the only part that's going to be used is the tangential component. In a similar way, the electric current source is N cross H2 minus H1. H2 is outside, H1 is inside. We are writing the total field, but because it's cross product with N, the only part that's going to be used is the tangential component of the fields. Again, this is real source and this is imaginary source. Nothing physically is called magnetic current. So if this is the actual problem, we have some sources and these sources are within certain region, and around this region we put like a surface, imaginary surface. Okay, those sources will produce radiated field E1 and E2 outside this surface, E1 and H1 outside in volume 2 outside the surface, E1 and H1 in volume 1 inside the surface. So this is the actual problem. This surface is an imaginary surface. You can draw any surface, and we want to find E1 and H1. The equivalent principle is saying that this actual problem is equivalent to this problem. So this is an equivalent problem. And we are saying that the field in volume 2 of this problem equal the field in volume 2 of the original problem of the equivalent problem under certain conditions, that the boundary conditions of the equivalence principle are satisfied. So this is the actual problem. This is an equivalent problem. In the equivalent problem, we'll put whatever field we want inside the volume, and then we put some boundary conditions on magnetic and electric current, surface current on this boundary, such that this surface current equal N cross H1 outside minus H inside, magnetic current minus N cross E1 outside minus E inside. So the equivalence principle is saying that the solution of this problem outside of S equal to the solution of the original problem at outside of S. Inside, we can do whatever modification we want, and notice that the sources now in the real problem, actual problem, doesn't exist. So the only sources that we have in the equivalent problem is the surface currents. So the solution of this problem is the same as the solution of the equivalent problem, but only in region 2, outside this imaginary surface. So this is like how the application of the equivalence principle look like. So further into this, like how can we use those principles that we talked about in solving problems. Okay, so here, this is a further modification of the equivalence theorem, which is Love's theorem. His name is Love. I think it's a French name. So here, just to make the problem simpler, we forced the field inside this imaginary surface to 0. So now the surface currents are just N cross E1, just N cross E1, and we neglect any source inside the surface, any current inside the surface, and this is Love's equivalent principle. It's a further modification to the equivalence principle. So also we have freedom in defining whatever medium inside the surface S. So if we have an electric conductor, the surface electric current will cancel out because of the image theorem, as we're gonna show in details, and the magnetic surface current will double, again because of the image theorem. If we have a magnetic conductor means a material with a very high conductivity, the magnetic current will cancel because of the image theorem, and the electric current will double because of the equivalence theorem, as we're gonna see. Those two cases can be used to solve the problem because we have like freedom in choosing the material inside surface S, but do no changes outside the surface. So we can put the same volume, same material. If this is whatever, medium 2, I can use the same media for this part, or I can assume electric conductor inside the surface, I can assume magnetic conductor inside the surface, and in all cases we have the equivalent problem, or now we're talking, because no source inside, we're talking about Love's equivalence principle applicable. Okay, why did we say that for electric conductor the electric current the electric surface current will cancel and the magnetic surface current will double. From image theorem, the boundary condition of perfect conductor, if we have surface current, electric surface current, the image will be the same distance from the surface and in the opposite side. When we talk about something on the surface, its image will be on the surface but in the opposite side, so we have the effect of the image theorem cancelling the electric surface current. For magnetic surface current, its image is along the same direction, so if we are bringing the magnetic surface current to the surface, the image will be the same, so it is doubled. The image theorem for perfect magnetic conductor, the electric surface current will have an image in the same direction. If we bring the electric current to the surface, the image will be next to it with the same direction, so it is doubling. The magnetic surface current has an image in the opposite direction. When it is on the surface, the negative part will be on the opposite direction and it cancels out. So now it's too many theories building on top of each other. We have Huygens principle, on top of it we have like uniqueness theorem, on top of it we have the equivalent principle, on top of the equivalent principle we had Love's equivalent principle, and on top of this we have the image theory used. So we are using like 5 different theories to simplify the problem. And for example, like here, like an explanation for what can be done. So the original problem, in this case, if we have like some surface current here, surface electric field, we'll have some magnetic current because of the presence of perfect conductor. The magnetic current will double, and we can use the equivalence principle, removing all of this and just use the surface current image theorem. We can just make everything the same media and replace the media, the conductor, with the image. So this problem and that problem, the original and the equivalent problem, does have the same solution in the right. In the left, we don't have a solution because we know inside a perfect conductor, no electric, no magnetic fields. So this original problem, after applying the image theorem, and we will have the equivalent problem, the solution of the equivalent and the original are the same to the right. To the left, we already know the solution, which is no fields inside a perfect conductor. So let us have this example here. The example is like this. We have an aperture waveguide, and this waveguide is like connected to a grounded sheet. So we have just an opening in a grounded sheet, and this sheet is a conductive sheet. So the waveguide aperture, this one, of course this is a cross section, is mounted on an infinite ground plane. Ground means connected to ground. Infinite plane, or it's very long or very large. As shown in figure, assume that the tangential component of the electric field over the aperture is known. So we have some tangential electric field on the aperture and are given, this is the symbol for it, find an equivalent problem that will yield the same fields E and H radiated by this aperture to the right of the interface. Because we know in left of the interface we have no radiation. So we are talking about the radiation here using the equivalent problem. So we want to formulate this into equivalent problem. So let us see how can we apply those theorems that we just learned. Okay, so here this is the original problem. With this problem I can use Love's theorem and have like an equivalent surface current. We have only tangential electric field, so we have only magnetic surface current. The electric surface current equals 0 because we don't have H tangential here. Okay, so in this case, this is like we're using Love's theorem or equivalent principle, and we are taking our surface, which is this left side. The volume that we are talking about is the left half space. So this is the problem. I can say, okay, I will fill the left half space with a conductor. So this would be an equivalent problem to this problem. Now, because here we have like nothing, no fields anywhere except on the aperture, so tangential field here is 0, so the tangential current everywhere is 0 except on the aperture. If we filled the left half space with a conductor, the image would double the magnetic surface current, and of course we don't have in this case any electric surface current. Even if it does exist, it will be cancelled out because of the image. So we reach the equivalent problem. We are saying the radiation from this equivalent problem and the radiation from this original problem in the right half space are the same. So problem, original problem, equivalence principle, Love's equivalent principle, applying image theorem, then the final equivalent problem. Solution of this problem to the right is the same as the solution of this problem here. Okay, how can we use this in a formal way to find the radiation equation? So this is the next part of the lecture. We know that from lecture 3 that we have sources. Here we are talking about surface current. We have either electric current, which is a real source, or magnetic current, which is an equivalent source. And we derived the far field equation based on the auxiliary functions. So we showed that the electric field, because of the A auxiliary function, when we have real current, electric current, with no magnetic or equivalent current, the radiation does have the electric field because of J, because of the electric current, does have this expression, and approximately it is minus J omega A. And then we did the derivation from A. We can say that the theta component is minus J omega A theta component, E phi minus J omega A phi. Again, this is an approximation. This is the exact expression. This is the approximation for the far field. From this approximation, we write down this component of electric field, and from the relation between electric field, magnetic field, and direction of propagation, in this case, of course, direction of propagation is AR, we can find H phi and H theta. So if we have electric current, we can, in the far field, we can approximate the field components into this format. Field components, because it's far field, it's transverse electromagnetic, we have theta and phi, we have phi and theta, no R component. Okay, so we derived those before in lecture number 3. If we have if we have J, we can find A by integrating over all the source area. Once we have A, as we show in the previous slide, we can find E and H, all the components. So if we have the source, in our case the source is a surface current, so that's why we are integrating over a surface. The auxiliary function A can be found, and from A we can find E and H. Remember that when we do, because we are integrating over some region, we have that R is the position vector of the observation point, R prime is the position vector of the source element, cosine psi is the angle between R prime and R. So we will see the geometry of the problem again, but we did this in lecture number 3. For phase parts, this is the approximations that we use, that R here equal R, which is the position vector, minus R prime cosine psi. R prime is the position vector of a source element. Cosine psi is the angle between the vector to the source element and the vector to the observation point. For amplitude element, we are using R approximately equal R small. So we take R outside, so we have e to the minus jkr. We take the R outside, it's 4 pi R, and then we have this integration. We can call this integration N, just for like shorter, for shorthand writing. We'll symbol to this integration of surface current over the surface of the source, or like the source surface, by N. So if we have J, we can find N, and we would say that A equal this expression. If we have A, then we have A theta, we have A phi. If we have A theta and A phi, we have, if A theta and A phi is like known, then we have E theta, E phi, H theta. So this is the sequence of finding A phi and A theta when we have just surface electric field. On the other hand, if we have surface magnetic current, MS, with no surface electric current, we'll have the auxiliary function F. And we have this approximation derived in lecture number 3, that H, because of the magnetic surface current or the magnetic current, does have this relation to the F auxiliary function. This is approximation for the far field. So H of theta equal minus j omega F theta, H of phi equal minus j omega F phi. E phi and E theta does have those expressions as we like did before. So if we have some, again, imaginary magnetic current or equivalent magnetic current, not a real, not a physical one, we can find F. And we use the same approximation for phase and amplitude. We can find, or like we can find the expression for F. This integration, we will give it a symbol L. So when we have just a magnetic current, we can find F, the auxiliary function, and the auxiliary function will have L, then F theta and F phi does have those expression, and if we have F theta and F phi, we can find H and E. And of course, if we have both magnetic current and electric current, the solution will be the superposition of the two solutions. So we just add like solution from first case, just having electric surface current, plus the solution of just having magnetic surface current, it will give us the total solution. So the summary of this, again, all of this had been shown in lecture number 3, but here we are giving a more specialized version of it that is applicable in an easier way for aperture antenna. So here, if we have electric current and magnetic current, E theta component will have this expression, E phi component will have this expression. Far field, of course, we don't have ER, we don't have HR. Same thing, we have expression for H theta and an expression for H phi. L is an integration, N is another integration, N depends on J, L depends on M. So this is the expression for N, which is J based. This is the expression for L, which is M based. So one thing here, we have like this in order, like if we go back to one of those vectors, sorry, those integration, so the element that defines the direction is this element. So to find L theta, we use M theta. L phi, we use M phi. So let us see here how this is being done. So for a surface, for example, if our surface is Cartesian surface, for theta, we need to write down the theta component. So this is the theta component in terms of x, y, z. So we have a conversion of the source, J or M, which we assume to be in Cartesian to the spherical coordinate. So this term here, you can call it J theta. If your surface is a sphere, it will be J theta, but if your surface is Cartesian, like as we're gonna see, it will have this expression. So you want to find theta, so you have the x component projected in theta, the y component projected on theta, the z component projected in theta direction, and in phi you will find that the x component projected in the phi, the y component projected on phi. Of course, z component projected in phi equals 0 because the pi is azimuthal while z is normal to this plane. Similar thing for M theta. This is the expression of M theta, which is the x component projected along theta, y component projected along theta, z component projected along theta. Here we have x and y component projected along phi. Of course, for the same reason, there is no z component projected along phi. Of course, you can just take all of this and write j theta. All of this, you write j phi, so on and so forth. So in summary, the procedure to solve a problem using equivalent theorem for aperture antenna or radiation from an aperture, we select a closed surface S over which the total electric and magnetic fields are known. From equivalence theorem, we can find the current J and M over S. We can define A and F, the auxiliary function, over the closed surface S. From A and F, we can find E and H. So those above steps are valid for any regions, for near field or far field outside surface surface S. But if the observation point is in the far field, so we can use the approximation that we had before, this approximation. This is the approximation for far field. And this is the summary of the procedure for how to find the radiated field from an aperture. So now let us work on applying what we learned about the radiation from aperture antenna on a rectangular aperture with ground plane, which is a very common configuration for aperture antenna. Before that, let us just remember the geometry of the problem. So the geometry of radiation problem, that we have like some source region and we are calculating the field at an observation point. The vector from origin to the to the source is r prime. The position vector to the observation is r. From source to observation is capital R. So this is the exact geometry, and here is the approximation. We approximate that the vector from source to observation is parallel to the position vector to the observation. So R capital, we are approximating it to be parallel to R small in the far field. And of course, because in the far field, R prime, which is the position vector of any point on the source region, is much smaller than R capital, much smaller than R. And we have two other approximations. The approximation for the phase term, which is R capital equal R small minus R prime cosine psi. Psi is the angle between the position vector to the source and the position vector to observation. So it's the angle between R and R prime. This is psi. And for amplitude term, we have R capital approximately equal R small. So this is very common, and we use it before for wire antenna, and we're going to use it here as well. So the geometry for rectangular aperture. So this case, we are taking the simplest case where we have uniform field on an aperture with a grounded plane, an aperture in a grounded plane. So this gray is a grounded plane. We assume that the aperture is in the XY plane. We assume that the uniform amplitude across this aperture is in the Y direction. It has a constant amplitude, and this is the method that we're going to use to solve the problem. This is the method that we are using to solve the problem. This is like the shape or the sketch that we used to like indicate the equivalence problem. We'll apply this here. So now the source that we have is some tangential component of electric field at different point. The vector from the origin to the observation to the source point is R prime. The vector from the origin to the observation point is small r. The vector from the differential source to the observation point is R capital, and we are like approximating R capital vector to be parallel to R small vector. The angle, as we said, between R prime and R is psi, is this angle. So now we go for the solution. The solution that we're going to apply is that we're going to take all the lower half space as a perfect conductor. We have only tangential electric field, so that we'll have only magnetic current. So for this magnetic current, and because of the ground plane, it will be doubled. So the magnetic current magnitude is 2 E naught, and it will be in the X direction. Why? Because the normal out of the N is out of the volume, so it is in the Z direction. The electric field is in the Y direction, so AZ cross AY, it will give us minus AX, and we have another minus sign here, M surface minus sign, so minus AZ cross AY, it will give us AX. So the magnetic surface current is twice E naught. It is in the X direction. And now we don't have J, of course, because it's a grounded plane. So even if there is some source for electric surface current, it will be zero because of the image theory. So now we need to calculate L theta. We just substitute in the expression. Mx has a value, My equals 0, Mz equals 0, and R prime cosine ipsi is the angle between, as we see here, is the angle between R prime and R. So R prime is in the xy, so we'll have just decompose R into the xy and have the dot product. So when we have the R, it's just the unit vector, it will be the R prime is x prime in the ax direction, y prime in the y direction. The unit vector across the capital R is sine theta cosine phi in the x direction, sine theta sine phi in the y direction. So R prime dot product with the unit vector along the capital R will give us this expression, which is R prime cosine ipsi here, and we are integrating this across ds prime. So we are integrating across dx prime, dy prime, depending on the dimension of the aperture, from x equal minus a over 2 to x equal a over 2, y equal minus b over 2 to plus b over 2. So y is from minus b over 2 to plus b over 2. X is from minus a over 2 up to x equal a over 2. So this is the limits of the integration, and this integration we can just separate it easily because we don't have anything, it's a uniform, so we don't have anything depending on x or y in the magnitude, just in the phase, so we can separate it, and this is very simple integration. This integration, just if we have like a phase integrated along dz, so this is the law, and we'll have L theta equal this expression. So it's sort of like a sinc function. Again, you need to do this math or trust it. It's you should do that. So the form of L theta will have some constants multiplied by cosine theta cosine phi multiplied by a sinc function related to x, a sinc function related to y. The x component equal k a over 2, k a over 2 sine theta cosine phi. The y, the capital Y, is k b over 2 sine theta sine phi. We do similar things for calculating L phi. We don't have my, we just have mx. So we just apply and we'll find another expression multiplied by the same two sinc functions. So now we have L theta, we have L phi. We can directly find E theta. We have this expression, and E phi. Of course, we don't have N. N is coming from electric current. We have no electric current, so it's 0. So E theta is related to L phi. E phi is related to L theta, and now we have the full expression for the radiated electric field from this uniform rectangular aperture. So we can just, for simplification, we can just have all the constants into C, where C equals this expression. Then it's multiplied by sine phi, sinc function, or E phi, which has cosine, sinc, and now we have all what we need, all the information that we need about the electric field, and if you know the electric field, you can find the magnetic field as we talked previously. So now one important definition here for antennas, something that I would like to share is the E-plane and H-plane. The E-plane is defined for a linearly polarized antenna. This is the plane that's containing the electric field vector and the direction of maximum radiation. H-plane is, again, for a linearly polarized antenna, is the plane containing the magnetic field vector H and the direction of maximum radiation. Why we are defining those? Because frequently it is referred to in the literature, and especially with rectangular aperture antenna. This is very common to talk about this. Okay, so for the E-plane, if you look for the field in phi equal 90, so phi equal 90 is the YZ plane, you will find that the E theta does have a value E phi equals 0, and in this plane, in the YZ plane, E theta is like a linear polarization because all the electric field in this plane is in the E theta direction. And so the peak, as we're going to see, the peak is along the Z axis. So the direction of the electric field is in the YZ plane, and the maximum is in the Z direction. So the E plane in this case is phi equal 90, or the YZ plane. So because phi equal 90, cosine phi equals 0, so think of 0 over 0. We need to differentiate both the numerator and denominator. We'll find that this sinc function will give us 1, as we all know. It's big when the angle here equals 0. So this will give us 1, and E theta will have this expression. While for E phi, because we have cosine phi here, phi equal 90, all the E phi component will vanish, and we just have E theta. So this is the definition of the E plane. So now we have the E plane, we have E theta. In the H plane, which is the XZ plane, we have the just E phi, so we have H theta. We'll have H theta and E phi equals 0 in the XZ plane, or phi equals 0 plane. And again, this is the definition of the H plane. We'll have like similar expression. Now we would like to find out where is the maximum. So the maximum in the E plane is the maximum of this expression, and this is happening when we have the maximum of this, which is when theta equals 0. So it is along the Z direction. Again, like the remaining part here is just talking about the sum of the mass. Okay, where are the nulls? So for E theta normalized equals 0, we need this function to equal 0, but the denominator doesn't equal 0. So this is happening when kb over 2 sine theta equal n by, where n doesn't equal 0. So it starts from 1. So for n equal 1, 2, 3, so the theta for null equals the sine minus 1 of 2n pi over kb, or if we just substitute k with 2 pi over lambda, we'll have n lambda over b. So those are the angles for possibility of having nulls. If we have very large aperture, so b is much larger than lambda, theta n will have just this happening every n lambda over b, 2 lambda over b, so on and so forth. This is an approximation, but just to have an idea how many nulls you would expect. So also we can find the beam width assuming that we have like symmetry around the maximum, the beam width equal 2 multiplied by theta maximum minus beam width. The beam widths might have multiple definition. We can have like beam widths between null. We can have half power beam widths. It can have multiple definitions as we talked before. So the null beam width is the angle, twice the angle between 0 and the first null. You can just follow the math. And so this is first null beam width, or beam widths between null, and this is a numerical example. If the width of the aperture is 5 lambda, we have another definition for the beam width, half power beam width, which is when the power is 3 dB below maximum, and we can just do the math. So you know the definition, we have the expression for E, you can find the beam widths between null, you can find the beam widths, half power beam widths, you can find the beam widths and multiply by 2, assuming that we have symmetry. And if you have like to find things exactly, you can just write a simple MATLAB code and you will find it. So it's just like some simple straightforward trigonometric math. So this is for you to play with the number and the expression and make sure that you can do that. Another parameter, again, we just have the electric field. We can do whatever we want. We can find directivity, we can find side loop level, we can find the location or the angle of the first side loop. We have the pattern, we can get all kind of information from this pattern. Here this slide is talking about first side loop. We can find its value, we can find its width. It starts at this minimum, first minimum or first null, and it ends at this second null, so on and so forth. So again, I'm not going to explain the math, but the idea should be clear. We have the pattern and we can extract any kind of information from the radiation pattern. So here's just like more and more examples explaining that. Again, side loop level, as we talked before, it's the ratio between the first side loop and the peak. Again, to see like how focused and clean our antenna pattern is. So here, this is a 3D pattern for like an antenna where the width in the x direction is 3 lambda, the length in the y direction is 2 lambda, and we would have this kind of field. We can like take this plane here, this is the E plane, or we can take this plane here, which is the H plane, and we can extract whatever information that we need for that. So this is relative amplitude. This is with ground plane, normalized antenna pattern. Okay, and this is, I think it's the same uniform plane wave, uniform ground plane. I think it's the same. Looks like it's a repeated slide, or I don't know. Oh, okay, yeah. There is a difference here, yes. B is 3 lambda. So here this is a square. This one is a rectangular. When it is a square, we have like a little bit different. So it's just like showing more patterns to have a feeling for it, or if you want to write a MATLAB code to generate such like a 3D radiation pattern. So the next topic is rectangular aperture with uniform distribution with no ground plane. Okay, so if we have just an aperture where we don't have a ground plane, what would we do? So there is a difficulty because both JS, surface electric current, and MS, magnetic surface current, will not be zero, and we'll have like fields coming from the electric current and fields coming from magnetic currents, and of course we add them up. So what kind of approximations that we would use for this? So the usual and most accurate relaxation or approximation is that to assume the surface field or the tangential field does exist over the opening only, and it is zero outside. By measurements and by other means, it had been shown that this is a good approximation. So our problem in this case is that without, or like this is with ground plane, we have just ms. So we have this expression. If you solve the problem without ground plane, you will find that we have a different expression. Why? Because we have, in this case, without ground plane, we have fields coming from J and other fields coming from M, and of course, like we add them to get the total radiated field from the aperture. Again, you can do the math. It's a long math, but it's a good exercise to find out this, or you can read it from the textbook. So uniform without a ground plane, we have like a clear difference between this case. This is 3 lambda by 2 lambda. So you can just do the math and find that. After that, we'll talk about like more practical cases. For example, here, rectangular aperture with TE10 mode. So the field distribution is the transverse electric 10 mode of the rectangular aperture. TE10, we just covered this in our microwave engineering course, and of course you can just look into the expression and find the consequence, and for simplicity we are studying by the case with ground plane. So the electric field expression, the electric field is in the y direction, and it does have a cosine distribution. Outside of the aperture, it is 0. So when we do the math, we'll find that E theta does have this expression. Again, this is just like applying this field and coming up with a solution. We can do this as an exercise. You can do like this for part of the homework, so on and so forth. But we can find E theta, we can find E phi in a straightforward way. With ground plane, we don't have J, we have just M. And here, instead of having uniform electric field, no, we have electric field distribution, and the remaining part is straightforward. Nothing like strange. Maybe like it's a little bit long derivation, but you can easily do it and find or get this expression. For y, because there is no variation with respect to y, the same sinc function, but because there is a variation in x, we have a separate or a different like function in the that is like dependency on x. So the E plane, which is again phi equal 90, we have this expression very similar to the case of uniform distribution. For the H plane, we have completely different expression than the case of uniform distribution. And again, for aperture, like the distribution of the field on the aperture is in many cases called illumination field. Illumination field. So here you can see, because we have a cosine distribution, we have like a smoother function. And anyway, this is for 3 lambda by 2 lambda. And here we have like some comparison. Okay, so here we have, one moment. So here we have like a comparison between the three different cases that we studied so far. Uniform distribution with ground plane. So this is the field distribution. Uniform distribution without ground plane. So this is the expression. We have electric field, and we may have also uniform distribution, and we have magnetic field as well. And the third case is TE10, which has this expression. So the electric field illumination here does have the same shape as this one, but this one does have a ground plane. This one, no ground plane. Here with a ground plane, but we have TE10 distribution. So the equivalent is that we have MX, surface magnetic current, on the aperture. Here we have a surface magnetic current on the aperture and electric surface current on the aperture. It's zero outside of the aperture. Here, because of the ground plane, we have the magnetic surface current only with no electric surface current. So now for the far field, the E theta does have this expression. Of course, in the far field, for all the cases, ER and HR equal 0, E theta does have this expression. Here, it does have like different expressions, so on and so forth, E phi. So you can do the derivation and exercise the difference to come up with like those solution here. So this is a good comparison. And the remaining of the comparison is in the next slide to talk about the beam width, first null, so on and so forth. One other topic that we would like to talk about is the effective aperture area of the aperture antenna. So we know that the effective aperture is used for example, effective area of the antenna is the effective aperture. It is in meter square. Power delivered to the load is BT. It's equals the incident power density incident, which is watt per meter square, multiplied by A effective. So A effective equal power delivered to the load divided by power density at the antenna. And we have this relation that we did before, that the maximum value for the effective aperture equal lambda square over 4 pi divided by the maximum directivity. So there is like a parameter for aperture antenna called the aperture efficiency. The aperture efficiency equal the maximum effective aperture divided by the physical aperture of the antenna. So for aperture antenna, the aperture efficiency is less than 1. The maximum effective antenna aperture is less than the physical antenna aperture. So for like wire antenna, we have the physical effective maximum effective antenna aperture is much greater than the physical, because like the physical is based on the cross section of the wire, which is very thin. So the aperture efficiency is much greater than 1. So this is just like studying more parameters of the antenna related to this case of aperture antenna. The beam efficiency, it is like the total power radiated in certain section divided by the total radiated power. So the beam efficiency can be used to judge the ability of the antenna to discriminate between signals received through its main loop and those through the minor loop. So if we take theta 1 to be the first null, it means that this is the total power concentrated in the main loop compared to the total power. So the higher the better. It means that it is more focused, or whatever energy that goes to the side loop is smaller. So talking about circular aperture, the same steps is very similar to what we did with rectangular aperture, but sometimes we use a cylindrical coordinate system, and sometimes you will see that the mass will produce the Bessel function. So it's a little bit different in its mass, but the procedure is the same. So it's an aperture, and on this aperture we do the same approximation, do the same procedure, but we are integrating over this circle. Same thing, calculating ms, calculating js. So what we did for rectangular aperture, we just do this expression. We have jx, jy, jz, and we solve the problem. For circular aperture, most of the time we describe the electric field as j rho, j phi. We have no jz. So how would we go for this? Because this is r, this is spherical coordinates, and this one here we need theta and phi, which is spherical coordinates. What we did here is we converted from Cartesian to spherical, and we solve it for theta and phi. So here, if the field is in cylindrical, what would we do? We convert from cylindrical to Cartesian, then from Cartesian to spherical. So it's two steps transformation. The mass will be longer. So like the theta will have this expression. Where this came from? This is converting from rho to x and y, and then use it. So this is, if you see this is the x component of the cylindrical coordinate system, which is this one here. So on so forth. So it has a component from x and y. This is the transformation from cylindrical to Cartesian, from Cartesian to spherical, and so on so forth. Here again, r prime is expressed in Cartesian, is expressed in cylindrical. So you convert from cylindrical to Cartesian, and then you do the dot product with r small. We'll have like a different expression, of course, and we are integrating over S, which is a circle. So when we do like the math, we'll see here we have like hybrid rectangular cylindrical case. So this is from X. We have this in cylindrical. So we express the R in cylindrical, and we express the field, sorry, the tangential field or the surface current in X and Y. So we can do like most of the time or all the time we'll have like dual coordinate system to deal with, sometimes triple coordinate system to deal with for the aperture antenna problems. So the remaining part, I will leave it to you to read it. I'm not planning anyway, like not to cover it in details, because we have like here, this is called Bessel function. I didn't talk about it before, but it's good for you to have some idea about that. The remaining part is, again, like it's the math. We're just doing like cases for uniform field, E field, E plane, then TE11 mode for circular aperture, so on and so forth. Then later on we'll have like an approximation, and then comparison between uniform distribution with ground plane, TE11 mode on ground plane, and at this point we'll stop. The remaining part is sort of like a reading material, and wish you all the good luck with this lecture.